Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for increments and differentials. Increments and differentials. So we use differential to approximate the increments of two different values of a function. So let me give you an example why this happens. So suppose that you have a function of two variables and every time you put two inputs, x and y, it will give you an output f of xy. Now the question is, suppose that you are taking measurements and you are putting your measurements, and usually the measurements have some error. So suppose that you have your measurement x and your measurement y, and you have some error that I'm going to call delta x and delta y. So obviously the value of the function is going to give you the value of the function of x and y, and the question is, well, how much is going to be the error due to the error in x and due to the error in y? That's something that we're going to use differentials to approximate the error of the value of the function. And for that, you guessed it, we're going to actually use the tangent plane. So the idea is the following. Suppose that you have f of your normal values, and these are the errors are delta x and delta y. Of course, if your errors are smaller, this approximation is going to be a good approximation, and well, I'm just blowing up delta x and delta y so you can see what's going on. So delta c is just going to be the difference between the value and the value with the errors. So it's going to be this one over here. That's going to be that difference. Now the thing that I'm saying is dc is going to be the difference between the value and the linear approximation with the errors that we have over here. So notice that these two things, the difference is one is taking into account the function and the other one is taking into account the linear approximation. Remember, the linear approximation actually approximates the function if delta x and delta y are small. So what's the thing that we have now? Let me just plug in what is the linear approximation. So the linear approximation is the value of the function times the derivative with respect to x, delta x, the derivative with respect to y, delta y. And when I subtract f of ab, the only thing that I have is this number right here that we're going to call the differential. So in this case, well, dx and dy are just going to represent placeholders for the difference, for delta x and delta y. So in other words, these two things are equal. And that's going to give us a formula that we're going to call the total differential. The total differential of a function of two variables is going to be described as dc equal to the partial derivative with x and y's, dx, this partial derivative with respect to y, dy. dx and dy are just placeholders. You will see how we're going to use them in just 1 second in our example. So this is the total differential. The total differential is going to be a formula. When you plug in things, it's going to give you approximation of differences. So notice that this formula actually comes from the equation of the tangent plane of a graph of a function of two variables. So the thing that we have here is this is the equation of the tangent plane, and we're sending f of ab to the other side. So the thing that we have is this is the difference in c. Let me just call it dc. This is the difference in x, and this is the difference in y. So notice that pretty much we're having exactly the same formula. We're seeing it in a little bit of a different way. So let me give you an example. A machinist has measured the height and radius of a cylindrical piece of metal, and it's 5.8 centimeters and 3.1 centimeters. 5.8 is in height and 3.1 in radius. So the measurements have an error of 0.02 in height, 0.002 in height and 0.001 in radius. So the question is approximately how much the volume is what's going to be the error in the volume if she just calculates the volume with the normal formula that we have. So first, our function is just the formula for the volume. Now we're going to find the total differential. I want to do that just to show you how the total differential is going to look like. So for that, we take the partial derivatives with respect to h and with respect to r. And the total differential is just going to be dv equal to the partial times dh plus the other partial dr. dh and dr are just placeholders for the differences, the difference in h and the difference in r. Now, in our particular case, we're going to start plugging in numbers in order to get at the end a number. So finally we need to plug in the difference and the values. So h is equal to 5.8, r is equal to 3.1, dh is the same as the difference in h, that is going to be 0.002, in other words the error, and dr is just going to be delta r, that is going to be the error in the radius, that is 0.001. So we plug in everything here and we have the radius, the error in h, then we have the radius h and the error in r, and that at the end is going to give you 0.173. So this is going to be an approximation of the error when you have these errors in your inputs. And that will be all. Thank you very much for your attention.